Thank you. So it's a great pleasure to be here. I'm very grateful for the invitation. Um, so I have an unconventional way of making slides. One aspect of this is that I encourage people to download the slides. This means, for example, that you can, if you forget how something is defined on a previous slide, you can just go back on your phone or laptop and look at it. So you can get these slides at maths.fan/ICTS.pdf. And that link is going to be, on most slides, that link is going to be up here. Okay, so I'm going to start nice and slowly. So this is the setting that we've seen before in several talks this week and last week. So we're looking at a system of polynomial equations to be solved in whole numbers. And specifically, I'm going to look at a system of homogeneous equations. There's going to be capital R of them. It's going to be capital R homogeneous forms throughout this talk. And they're going to be in S variables. And that also is going to be consistent throughout the talk. So if the number of variables ever appears to be N, that's a typo. The number of variables is always S. Okay, and at least at first, we're going to look at forms with integer coefficients, although later on, we're going to talk also about forms with real coefficients. So the system of equations then is f equals 0, so it's a system of R equations in S variables. And we're going to solve it in whole numbers, and those whole numbers are going to have size b. B is going to be a big parameter throughout the talk. Again, occasionally later on there's going to be some other parameter like a capital P or something, but b is always going to be a large number that tends to infinity. So what answer should we expect? I've said that the question we're asking is how many solutions are there in whole numbers of size b? So what answer should we expect? We have sophisticated predictions, but just to remind you of the basic idea, the form fi has degree di. So the variables go up to size, the variables are of size capital B, and so the form has size around capital B to the di. The variables are whole numbers, the coefficients are whole numbers, so form fi. It's a whole number of size around capital B to the di. So we look at the number of possibilities for the whole vector, and it's the product of the number of possibilities for each component fi, so that's b to the sum of the degrees. So we might guess that since this is the collection of values it ranges over, maybe it's roughly equidistributed on those in some very hand-wavy sense. So maybe it's 0 around 1 over b to the sum of the degrees at the time. So there are about b to the s tuples of integers of size capital B, and so that suggests that we should have about this many solutions. So this can't be quite right. So here the text turns orange when I'm about to get rid of it, which I'm not always completely consistent about, but I do my best. And so if there's something in the orange text that you wanted to ask about, then when you see it turn orange, you should speak up, or if you want to go back and look at it, then you should download the notes. Okay, so let's make this slightly more rigorous and slightly more precise. So this is now the counting function. This is the number of, so when I say whole numbers of size capital B, I'm now being precise and saying that I mean whole numbers between minus b and b. And so this is the counting function that we're looking at, and I'm excluding 0. So again, I'm trying to be consistent about that. So if you see the counting function include the 0 vector at some point, that's a typo. This is the counting function that we're looking at, the number of solutions to f equals 0, where the variables range over integer points in this box except for 0. 0 being a trivial solution because the forms are homogeneous. Okay, so our slightly more precise prediction is going to be that we model the variables by the vector of integer variables by a random real vector in the same box. And our random model for the polynomials is then going to be given by taking the integer part of the polynomials evaluated at that random real vector. that model predicts, so we get about 2b to the s bites at the cherry, we get about 2b to the s things in here where f might be equal to 0. In this random model, this is the probability that each one of them is equal to 0. And so our prediction is this much. And the typical size of this prediction is some constant depending on f times this b to the s minus di. So this can't be quite right because we could have a p-adic obstruction. So for example, this polynomial doesn't have any non-zero integer zeros because all the variables would have to be congruent to 0 mod 2 and then mod 4 and then mod 8 and so on. So we fix that by repeating this same construction over zp for each p as well as over r, and we get this prediction. And so when the circle method works, this is typically the answer that it's going to give you for the number of zeros of these forms. Okay, so I've just rearranged what was on the last slide and removed some notation in order to just be completely clear about my big O notation here. So less than is bounded by some constant, big O is bounded by some constant. Smiley frowny face but it's true both ways. And twiddles is the limit tends to 1, and little o is the limit tends to 0. And that these last two are always as capital B tends to infinity, so I'm generally not going to say that. Okay, so this thing that the circle method proves when it works is called the analytic Hasse principle, or at least that's what I'm calling it today. And it's a case of the Manin-Pair conjecture, which is a sort of I think of at least as a more sophisticated version of this prediction. Okay, so now I'm going to clear some room. So I'm going to, at the end of the talk, I'm going to give a more technical account of the proofs of the results that I'm going to speak on. At this point, I just want to give a really just quick reminder of what the circle method looks like. So this is the thing that we're trying to estimate, the number of whole number solutions to this system of equations. So here I've forgotten to exclude 0, but that's fine because I would have added it back in again here anyway, so that's fine. So okay, exclude 0 here and write +1 here, it's the same thing. So we write it as the integral over the unit hypercube, the r-dimensional unit hypercube of this exponential sum here. Sum of the integer points of subnorm going up to b. So that's the integer points in our box, so that should be a b up there. So that's integer points in our box. And of e to the 2 pi I t dot the polynomials evaluated at that integer point. And then this exponential sum typically looks like this graph down here. So this is a one-dimensional example. So you have some big peaks at regular points, quite nicely shaped peaks. You can actually, so here at 10 is a peak with leading constant 0. So that's also a peak, it's just a peak of height 0, which might not be immediately obvious, but if I'd taken a few more terms, you'd be able to see that it's particularly nicely shaped around there. Then in between those peaks, it looks pretty random, and in particular, it looks pretty small. And so the fundamental idea of the classical circle method is we're going to try and prove those two claims I've just made. We're going to try and prove that this exponential sum has some big peaks for certain values of t with a nice predictable shape. And in between those big peaks, it's small. Right. And in particular, in between those big peaks, there's some size about square root of the trivial bound that it could always be. So you see here that's around 10, where it could basically always be of size around 10. So we're not going to be able to prove an upper bound much better than 10, but we want to show that it's small in between the peaks in some sense. Okay. Yeah, actually, here I should have put in, so I went to the Science and Technology Museum, maybe it's called, in downtown in Bengaluru, and they have a very nice, they have, most of the galleries are actually named after a field of science, right? So you have like the biotechnology gallery and so on, and then the maths gallery is called the Fun Science Gallery, which is good. And they have there a very nice collection of pendulums, which you can swing to see them go in and out of sync, which is essentially just the same thing that's happening here. So maybe I should have put that here, so that you can watch this thing sort of evolve, and the nice well-shaped peaks are when all the pendulums swing in sync, and yeah, this is very satisfying. Okay, so what conclusions do we get from this method? So the classical one and the starting point for the results I'm discussing in this talk is this result of Birch. So I think in some other talks this was cited as 1961. The reason is that back in those days, peer review happened so quickly that it was not common for a paper to be submitted in one year and published in the next. And so there's an ambiguity. Happy days. Okay. So so if we get this asymptotic that we want, so here I've compressed the complicated prediction into a constant times a power of b. So we get this asymptotic that we want, provided that the system of polynomials f is smooth. And smooth means geometrically smooth, so I put what that means up here. F equals 0 defines a smooth manifold away from the origin over the algebraic closure, and smooth variety away from the origin and the algebraic closure. So if f is geometrically nice, if it's smooth, and all the degrees of all the forms are the same, so we only have forms at 1 degree d, which is why this prediction looks like s minus dr instead of s minus sum of the degrees. And the number of, then all we need is for the number of variables to be sufficiently big. And we actually had this, a requirement of that shape even to make the conjecture. I didn't really say it out loud, but for the conjecture to make any sense, S needs to be bigger than the sum of the degrees. So this ought to be a big number for the prediction to be a reasonable prediction. If it's a small number, then we don't really know what the answer should be by these methods. And actually, S should be more than twice the sum of the degrees. Otherwise, the more advanced version of the prediction, that's the Mannion pair conjecture, would have to be used instead. So actually, we only really expect a result of this shape here if S is bigger than twice the sum of the degrees. That is, S is at least 2dr plus 1. And okay, I mean, this doesn't look all that different in shape from 2dr plus 1. It's at least 2 to the something times around d times a polynomial in R plus something. It looks promisingly similar to what we conjecture should be the optimal condition here. Right. So here's that optimal range again. There's been tremendous study and interest in the case of a single form. So a lot of really exciting work, but too much for me to summarize here. What I will talk about is the work that really has this shape. So really looks at proving this asymptotic whenever f is smooth, the degrees are all the same, and the number of variables is sufficiently big, and the number of forms R is at least 2. So this case of 2 quadratic forms was already discussed by Pankaj yesterday. So currently there's this nested delta method of Munshi. And in Pankaj's talk, he discussed an approach that would reduce the number of variables by 1 with a 2-dimensional delta method. He also, I think, already mentioned this result obtained by repulsion. and there's an analog for degree 3. So you can get an improvement on Birch's number of variables. You can reduce the number of variables needed for systems of, I think this is better for systems of 3 or more cubic forms, and then for systems of 2 cubic forms, there's this result of Northy and Vichy. So there are also, and I think some of these may have already been mentioned, so there are also some results which don't apply, which don't quite fit in under this heading, in the sense that the statement is not identical to this one with a different number of variables. They have some stronger condition on F than it just being smooth. It has to have some special form. But the methods used are closely related, and for that reason I list them here. Heath, Brown, Pearce do systems of 2 forms which are split in 10 variables, and then the same general idea, although it turns out to be quite a lot more complicated in some parts, was used by Pearce, Schindler, and Wood to handle systems of 3 quadratic forms in 20 variables that are suitably split. Browning, Pearce, and Schindler use, so this was the approach that Tim Browning asked about after Pancosh's talk yesterday. So this uses the idea of taking the one-dimensional delta method over a number field and using it to solve a problem over, for example, Q. And in certain cases, this can handle a system of R quadratic forms in as few as 6 R variables. So all of those examples were improving the number of variables while keeping maybe some small variation to the condition on F, but they all kept the condition that the degrees should be the same. There are also generalizations of this theorem which no longer have the requirement that the degrees are all the same. These are in somehow not in chronological order. So the original result of this form was a result of Schmidt, which had some write-downable but quite large number of variables. This was much improved by Browning and Heath-Brown. So in many special cases, the number of variables is less than this, where by special cases I mean for particular choices of the degrees. So for example, if you choose sort of many quadratic forms and one form of degree D, something like this. In the sort of generic case where you have comparable number of forms in every degree between 1 and D, so maximal degree D, and maybe comparable numbers of forms with every degree going up between D by 2 and D, something like that, then the number of variables is roughly looking like this. The exact number of variables is again fairly elaborate to state, but typically it's around this size if you don't have any special properties of the vector of degrees. In particular, what I want to observe here is this does look pretty similar to this in the sense that there is an exponential, but it's only of size around 2 to the D. It's quadratic in the number of forms, and then the real change between this and this is that here we have a linear polynomial in D, and here we have a cubic one, and after all it's multiplied by an exponential, so maybe we think that D cubed times 2 to the D is not so very different from D times 2 to the D anyway. So this is a very satisfying improvement. And in special cases, one can do even better than that. There was pre-existing work on a system of one quadratic and one cubic form by Browning, Diebman, and Heath-Brown. Okay, so just rearranging this content a bit. This is the result that I'm advertising in this case. So I've just written an inequality here, and what I mean is that you can substitute this for this. So the You can remove the assumption that the degrees are all the same as long as f is smooth and the number of variables is this big. We get this. We get the asymptotic that we expect. B to the s minus the sum of the degrees. Okay. So this is write-downable, but it's still fairly complicated and maybe not obvious at first sight how big it is. In what I think of as the typical case, where maybe we have roughly equal numbers of forms in every degree between d by 2 and d, this has size about 3 to the 2d squared times r. So that's pretty big. In particular, I mean, it's big enough actually that I think I absorbed one can be a bit more precise and make it be a polynomial in d times an exponential, but I think I decided it was just big O of 3 to the 2d squared anyway. So that is, the exponential dependence is quite a lot worse. So it's 3 to the 2d squared is quite a lot bigger than 2 to the d as d grows. On the other hand, it is linear in R, and so when the number of forms is really big, this is going to be an improvement. Although, you know, it's going to need to be pretty big. On the other hand, when all the degrees are the same, then this is actually a reasonable number. So when all the degrees are the same, this d minus di destroys this power of 3, and then this becomes 1 to the, this becomes dr2 to the d plus r, which actually generalizes the previous results that I obtained by the repulsion method. So this 9r for cubic forms and 9r for quadratic forms and 25r for cubic forms are matched by this, which is not a coincidence. Okay. So in particular, this improves Birch's result as soon as, so this matches previous results for the degree forms of all degree 2 and forms of all degree 3. And if the degree is bigger than 3, then this improves on Birch as soon as we have even a system of 2 forms. Okay. So what does this look like? And actually, that case, when the degrees were all the same, I even announced before at Hausdorff Summer School. And okay, there have been some delays in writing it up, partly because the differing degrees took a lot longer than I expected. Okay. So what does this look like for a concrete case with differing degrees? So if we take the case of one quadratic and one cubic form, it's about 6,000 variables. So as soon as the degrees start differing, this is a pretty big number. In particular, okay, the 6,000 is bigger than 29. In my original phrasing of this sentence, it looked like I was attributing to Browning, Diekman, and Heath-Brown the theorem that 6,000 is bigger than 29. But okay, so this is more in the realm of the kinds of number. As soon as the degrees start differing, this is more in the realm of the kinds of number that you see in earlier work that used different methods, like the result of Schmidt would still use the circle method, but in a slightly different way that got bigger numbers of variables. Right. So how am I able to obtain this? So the really key ideas, I mean, there's a use of the pigeonhole principle at some point, which took me a while to think of, but I don't think that makes it particularly deep. I think the really key ideas here are p-adic repulsion, which was explored in those Hausdorff lectures I previously mentioned, if you want to read more about it. And a way to extract lower order terms in exponential sums. And I'll tell you more later in this talk about what that means, but what I'm thinking here is that we'll have some exponential sum and we want to get a bound for it that only depends on lower degree terms in the polynomial. So an exponential sum over a polynomial, and we want to get a bound. Maybe it's a polynomial of degree 3, and we want to bound the exponential sum only in terms of the degree 2 part. Okay. So before I say more about that, I want to say something about another application of these ideas, which is that they also work for forms with real coefficients. So the character of the result you get is different in this case. So you get a result typically for, well, I think the preferred kind of result to aim for is this one. So here I look for solutions to a Diophantine inequality. So I take now a system of R forms in S variables of various degrees di, but now with real coefficients, and I'll call them G instead of F to indicate that, to remind you that they have real and not necessarily rational coefficients. In fact, they won't have rational coefficients. And then instead of looking at G of X equal to 0, which would probably never have any integer solutions, we'll look at G of X has subnorm at most 1. So each form Gi lies between -1 and 1. And the interval -1, 1 is kind of arbitrary here. One could use a different interval. And so we'll look for small values of these forms with the variables being integers of between -b and b. All right. And here's just an equivalent formulation of the idea of G being smooth. So this is just the same thing as being smooth from earlier. I probably should be saying smooth and not non-singular. Okay. So this is sort of analog of the counting function n of b from before. And one can try to use similar methods to estimate it. One difference is that whereas the circle method is for results of the kind that I stated, where you want this asymptotic formula as soon as the thing is non-singular and the number of variables is sufficiently large, the circle method is sort of a leading approach. It's one of the go-to methods. And for this kind of problem, the circle method has there are some difficulties in applying it, and so one of the leading methods instead is to use methods. One of the leading approaches instead is to use methods from ergodic theory. So this was more or less introduced by Margulis, working on the Oppenheim conjecture. And it leads to a result like this. So this is the kind of degree 2 R equals 1 case. So you get the asymptotic that's predicted here. So this is the prediction from before without any p-adic corrections, which makes sense because there shouldn't be anything p-adic going on here. So I'm assuming here that G is not a multiple of any form with rational coefficients, so it's irrational in a sense. And then there aren't any congruences modulo any powers of any primes that can come into play. And so here we have the original naive prediction. And that is, in fact, an asymptotic for the counting function as long as the number of variables is at least 5. Okay. So in fact, these methods work for smaller numbers of variables as well. And depending on your point of view, you could say that they give an asymptotic. The asymptotic that I've written here is not true for all forms of degree 2 in 4 variables, and so one should correct the prediction somehow. Yes. Okay. So I'm going to remove this theorem from the screen now. Although, of course, you can still get it up here. And talk about results using the circle method. So this sort of goes back to the work of Benkes and Goetze, who used circle method to give an alternative proof of this result. It's a bit more than maybe I should have been more praiseful here. So the thing is that it's more effective. The ergodic methods are not necessarily effective at all, whereas this is sort of automatically effective in a way which depends on the Diophantine properties of the coefficients of the polynomials. So they reproved this result when the number of variables is at least 9, so a bit larger than 5. And this was then, these ideas were then used by Muller to give a version with a system of R quadratic forms. So we have now this irrationality condition. So I'm going to call a system of real forms irrational if no non-trivial real linear combination of them has integer coefficients. So if this were to fail, if there were a non-trivial linear combination of these with integer coefficients, then these inequalities where we require all of the g's to be between -1 and 1, these would hide a finite collection of Diophantine equations. And so we wouldn't really be looking at inequalities, we'd be looking at equations, and so that's the reason to impose this irrationality condition. In particular, this asymptotic, you don't expect it to hold without this condition. So if you have this necessary irrationality condition and you have a non-singular, so geometrically nice collection of quadratic forms in at least 9 R variables, then you get the expected asymptotic. So this 9R flashed past on a previous slide in a result about quadratic forms with integer coefficients, and this is no coincidence. The method is in some sense the same. And at least on the minor arcs, you could say the method is the same. So this was an exciting version. This result of Banks and Goetze caused some excitement. This version of the circle method that they introduced was standardized and more sort of typical number theory, modern number theory notation for the circle method was applied to it by Freeman. Who used it to prove various results for systems of diagonal forms. Then I should also mention this more recent and very intriguing work, very difficult, but I think quite exciting, which reproves the result that Eskin, Margulis, and Moses got by ergodic methods. By the circle method, which means that it's explicit in the Diophantine properties of the coefficients. And the idea of this proof is very subtle and very intriguing, which is to bound some exponential sums by certain nice functions on one-parameter groups. So the exponential sum is a function of a parameter called maybe alpha, and the idea is that exponential sum S of alpha kind of factors through a one-parameter group. So you map alpha into a one-parameter group and then bound S of alpha by a nice function on that one-parameter group. So this I find particularly intriguing because it's work of Ben Green on one quadratic form in 8 prime variables, which actually does something suspiciously similar, but instead of being a one-parameter Lie group, it's the points over a finite ring on an algebraic group. But okay, they're both algebraic groups. It's just here we look at the real points. There they look at there Ben Green looks at the points defined over a finite ring. It's sort of intriguingly similar. The formal structure of the proof is remarkably similar, even though all the details are different. So I think there's probably some very interesting things hiding in there. Oh yes, thank you very much. That should be a -2R. Thank you for pointing that out. Okay. So higher degrees, yes. So for higher degrees, we have, so I mentioned that Freeman had worked on the diagonal case, and this is mostly about higher degrees. In fact, there's quite a large literature on the diagonal case, which I didn't discuss at all in the case of forms with integer coefficients. But okay, the field is a bit thinner here, so I might as well put it in. Not least because apart from the quadratic case, asymptotics for this problem are essentially only known in certain diagonal cases, as well as certain rather special cases, certain particular families of cubic forms. Other than that, all we have is lower bounds for this counting function when the S is extremely large, and results that say there is a non-trivial solution when S is, again, at least write-downable, but pretty large. Okay. So there's fewer methods, fewer results in the higher degree case. And so here I give a result that applies with higher degrees, and also for so this applies with higher degrees and also for systems with differing degrees. I think I kind of assume here that all the degrees are at least 2. Actually, with forms with real coefficients, the distribution of one higher degree polynomial and also a linear form, the joint distribution of these is interesting. So if you allow linear forms, there actually are some results with differing degrees. But if we just follow the convention for now that all the degrees are at least 2, then these results all have, we have these results which all have the degrees being the same. Whereas this allows differing degrees, and the number of variables is very similar to what it was in the integer case. So this blue part is new, it makes the result worse, but the red part is exactly the same as it was before. So we have an extra factor of the maximum of d minus 2 and 1, and so this is a little bit bigger when the degree is big, when the degrees are big. And then we have the same asymptotic. Just putting the notation back on the screen. So this is the general theorem, and in some sense, so in some sense, the surprise here might actually be the number of variables is different at all, because in the quadratic case, Muller's result translated into the same number of variables for forms with quadratic systems of quadratic forms with integer coefficients as for systems of quadratic forms with real coefficients. And it's a bit bigger here because in the case of forms with real coefficients, we can't use p-adic propulsion, and so we can't get the little saving that provides. Okay. So I have 10 minutes, and I should say something about the proof. So what I'm going to do is I'm going to skip to the part about detecting lower degree terms, because I think that can be at least stated in a way that can be understood in 10 minutes. I can also say something about how repulsion works in general, but this is kind of an interesting new ingredient, and I'd be curious to I think there are some similar results out there that I ought to sort of study and compare this to, but which I haven't necessarily located yet. So I guess I'm not claiming that this is new in every case, actually. So here we have some typical notation for the circle method. So E of t is e to the 2 pi I t. This forward difference operator, it takes a function, shifts it by h, and then subtracts the original function. And if you apply it r times, then we write that more concisely by just putting all the shifts in a row with one symbol for the operator. I'm going to also use these superscript square brackets to indicate taking the degree k part of a polynomial. And if I apply this forward difference operator k times to a degree k polynomial, then what I get actually is independent of the x variables. And so although f is a polynomial in x, and normally when you apply the forward difference operator, you get another polynomial in x. If I take a degree k polynomial and I apply the forward difference operator k times, I don't get a polynomial in x. I get something that is constant when considered as a polynomial in x, and so actually doesn't depend on x at all. Instead, it's a multilinear form in these k vectors of variables. So this multilinear form comes up constantly in the circle method because it's what you get when you apply Weyl differencing to an exponential sum in the polynomial. Okay. So then let's take a look at this funny looking proposition. So on the left-hand side, inside the absolute value, we have a typical exponential sum of the kind that we would like to understand in the circle method. So this is the thing I put up with the pretty picture before, except that it's got a smooth weight, which is handy for the analysis and necessary when doing real coefficients. So this is just some compactly supported smooth weight. The way that I've written this is given a weight, there exists a weight, and I guess it should be taken as read that somehow this weight depends in a reasonable fashion on this weight. For example, all of the values, support, and derivatives of this W twiddles are bounded in terms only of some upper bounds for the value, support, and derivatives of this weight W. And in fact, one could write this weight explicitly. It's just not very enlightening. Okay. So you can think of both of these as just some fixed smooth weights. And then we have some polynomial f of degree at most d, and we want to extract the degree k part of that polynomial. So this is all in s variables. And so what I do is I raise this to some extremely large power. So this, by the way, is a normalized exponential sum. So maybe this 1 over b to the s wasn't in it the way I stated it before. So this is normalized by 1 over b to the s, and so the thing that's inside the absolute values here, the trivial bound for this thing is its big O of 1. There are about b to the s summands, and I've got a 1 over b to the s here. So this is normalized to have size at most big O of 1, which just lets us state things in a cleaner way. And so these things also are normalized to have trivial bound big O of 1. Okay, so in the classical circle method of Birch, what one would do here is one would take k equal to d. One would raise this to the power of 2 to the d minus 1, so the way that this is stated, that doesn't make sense actually. So like if k was equal to d, we would have like a minus 1 here, and this would be not a whole number, and nothing would make sense. So in the classical case, we would take k equal to d here. We would just raise this to the power of 2 to the d minus 1, so just this first thing before the plus and ignore everything else. And then we would get this upper bound here. So we would raise it to the power of some reasonable number, 2 to the d minus 1, and then we would get actually both of these bounds here with k equal to d. So when k is equal to d, this is classical. We need a much more reasonable exponent here. And what we would get is, so first we get a bound in terms of this multilinear form. And so here there's no x. So I'm using the fact that this doesn't depend on x. There is in fact no x here. X is not defined at this point. We just have the vectors h1 up to hk. And so what this is here, okay, there are some absolute values, but never mind those. What this is here is this is an exponential sum over this multilinear form. The absolute values are not so important. So this is an exponential sum over this homogeneous multilinear form that only depends on the degree, in that case, d part. And because it's a multilinear exponential sum, it's very nice. It can be understood very well. The part inside the absolute value we can basically evaluate using Poisson summation, and that gives us this upper bound here, which is in terms of a counting function, where here we're looking at, so m is the, so what m is the vector of coefficients of this multilinear form considered as a linear form in the last vector. So I guess I should, I'll write that on the board since I didn't put that on this slide. So m, my notation here is fk h1 up to hk minus 1. This is the vector of coefficients of forward difference operator h1 up to hk minus 1, and then some vector applied to f. I go forward again. And so in particular, so what I mean here with this dot, this expression here is multilinear in the k vectors here. In particular, it's a linear form in the last of these vectors. And so by considering it as a function of that last vector, we can consider it itself as a vector. And that's the vector m. So this vector m is just the derivative of the gradient of this with respect to the last vector hk. So that's another way of writing it, is that it's the gradient with respect to hk of the forward difference operator h1 up to hk f. So here we have this, this vector of multilinear forms. So this is now a vector of degree k minus 1 multilinear forms, being within a distance 1 over b of an integer vector u. So this is counting values of h1 up to hk minus 1, such that this vector of multilinear forms is very close to an integer vector. So that's, in particular, so this is a nice sort of multilinear counting function. So this is what geometry of this is what Weil differencing gives you when applied to this exponential sum in the degree d case. And this is the insight of Davenport, which Birch built on, was that this is very well prepared for an application of the geometry of numbers. Okay, and so what this does is it says, well, if I make the power here much bigger, a lot bigger than 2 to the d minus 1, then actually I can get the same character of result, but instead of capturing something about the degree d part here, it captures the same thing about a lower degree term. So somehow, once one has this result, in some sense, one can just insert this into, in some sense, one can just insert this into the existing repulsion argument and turn the handle. So in some sense, if one thinks about, if one looks at how repulsion works, this type of result is precisely what's needed in order to apply it to systems with differing degrees. Okay, thank you.
Thank you, Simon, for a nice talk. Are there any questions? Can I ask a question? So I think you didn't, what is, so why is p-adic repulsion better than the real one?
Good question. So, once one's applied Weyl differencing, the whole thing becomes transformed into a problem involving various multilinear counting functions. So in repulsion, so here on one slide is a summary of the whole repulsion argument. So it's a little dense. But the idea here is that, so let's go backwards from the conclusion we want. So we want this asymptotic for the counting function. Define this exponential sum up here. So this is the normalized exponential sum from the slide we were looking at a moment ago. So what we want is we want to show that, oh, because it's normalized, there shouldn't be an S there. Whoops. So look at this super level set, the set of points where this exponential sum has big absolute value. What we want to show is that the set of linear combinations of f for which this exponential sum has big absolute value has small measure. So this exponential sum rarely has big peaks. What repulsion does is it hands you a result of this shape, that this exponential sum is rarely big. It's large only at certain large well-separated peaks. And it hands you that provided you can get an upper bound for some other multilinear counting function. So this looks very similar to the counting function we had on the previous slide, but it's subtly different. So here, instead of asking for this vector m to be close to a vector of integers, we just ask for it to be small. So this is counting solution. This is counting k-1 tuples of integer vectors, such that this vector of multilinear forms is small. And if you can get a good upper bound for this counting function, then you can turn the handle on the repulsion argument, and it runs all the way through. It gives you some bound for the measure of this sets, measure of these sets where the exponential sum is big. How good the quality of that bound depends on the quality of bound you can get for this counting function. If you can get a good enough bound for this counting function, then you win. Okay, so that's how repulsion works. So this is actually, this is real repulsion. This is not p-adic repulsion. And so when I say small, I just mean small in the ordinary sense. So this should be like the subnorm of this vector or something. Okay. So p-adic repulsion looks a tiny bit different. Instead of asking for this vector of multilinear forms to be small in Archimedean sense, now it has. Now we're looking at it for a polynomial f which has integer coefficients, and we want it to be. I guess this should be. I guess this should be a. Okay, yeah. So there should be some the sign. There's a sign error here. Never mind. So instead, we want it to be congruent to 0 modulo some power of p. So we want it to be congruent to 0 modulo some power of some prime. Okay, and so that is somehow an non-Archimedean version of the same problem. Instead of asking for this vector of multilinear forms to be small, we ask it for it to be divisible by some prime. But there's a big difference, which is that estimating the number of solutions to some random multilinear inequality. It could be difficult. The bound you get might not be very good. Whereas if you want to count the number of solutions to a congruence mod P, we know how to do this. You sort of pick up a textbook and you use standard bounds for the number of points on a variety over FP. And so this is the reason that p-adic repulsion is better. It's because your auxiliary counting problem that you need to handle is just counting solutions to a congruence mod P.
Okay, thank you. Are there any other quick questions? If not, then let's thank Simon again.